So I will be talking about how I use dwarf galaxies, which you can see a few pictures of those here, to study the fundamental physics of dark matter. So if we were able to see dark matter, which we can't in the universe would look something like this. So what you're looking at is a dark matter simulation, gravity only. And you can see the filamentary structure, which we call the cosmic web, filling the space of the universe. The bright spots you are seeing here, the color scale is just doing put bright spots on high density region. So these are not actual galaxies, but these are the places which we believe the galaxy will form eventually. And so you can see this rich structure of dark matter connecting places which we think the galaxy will be forming. And my goal is to using the property and distribution of galaxies to study the nature of dark matter. So if I were able to play this picture as a function of time, this will be what it looks like. So the universe starting with a pretty homogeneous state, and the gravity, because of a small perturbation in the beginning, start to pull slightly over dense region together. And with time, you can see they start to form these bright spots, which, as I mentioned earlier, just high density region of dark matter. We call this dark matter halos. The halo keep merging and grow with time. And this strong gravitational pull also pulling gas, hydrogen in the universe. And then so eventually ignite to form stars and galaxies. And so the cosmology, like the composition of dark matter, dark energy, and no matter, dictates how this kind of structural formation, I guess, vary as a function of time, and hence have an imprint in the final galaxy distribution in our universe. So what is dark matter? We still don't quite know what dark matter is. And I mean, in the past, I guess, decade or even 2 decades, we have been working very hard trying to find out exactly what it is. And so there are many particle experiments that are searching for dark matter. And in this very cute cartoon, they actually show you 3 distinct methods that people are trying to find dark matter, including direct detection, where we put a director underground so that only dark matter particles are more likely to pass to hit a director to produce a signal. Indirect detection, where we are searching for gamma rays that we hope to produce by annihilation of dark matter particles. And also through collider, this one at the Large Hadron Collider, we are colliding protons and hoping to turn energy into dark matter particles. And so all these different particle experiments are ways that we search for, I guess, the signal of dark matter, but we haven't found any through these methods so far. On the other hand, we have been using galaxies and other astronomical observation to indirectly, I guess, provide evidence to the existence of dark matter. And so the question here is that, can we take one step further to not only provide evidence, but actually put constraints on the particle nature or non-particle nature of dark matter through observation of galaxies and other astronomical probes. And so my particular research lies in using galaxies. There are many other astrophysical probes that we can use to study dark matter. But for the use of galaxy, the main challenge basically lies in, I would say, 2 particular things. One is the uncertainty in the galaxy-halo connection. So as I mentioned, in this very simple picture of galaxy formation, the galaxy forms within dark matter halos, but there's a lot more physics involved in the formation of a galaxy. And so understanding how galaxy forms become critical, because that is one of the biggest systematic uncertainty when you try to use galaxy statistics to infer the dark matter structure. The other thing is just, it's difficult to find very faint galaxies. And I was just, in my next slide, I will show you why faint galaxies is particularly interesting. But finding of these smaller galaxies actually are more informative. In some particular cases, are more informative to different dark matter models. And so finding those galaxies is another observational challenge that we have if we want to use galaxy population to study for the nature of dark matter. So why we want to find small galaxies? So dwarf galaxies in particular are sensitive to different documented models. And here I'm kind of equating dwarf galaxy with substructures. They are a slightly different concept. One is actual galaxies, and the other is the dark substructures surrounding those galaxies. And so you are looking at 3 pictures of, again, dark matter simulation with slightly different dark matter model. This one is a cold dark matter, this one is self-interacting dark matter, and this one on the right is warm dark matter. And so you can see they have slightly different imprints of the final substructure where we believe those would be places hosting those small dwarf galaxies. You can see very clearly in the case of warm dark matter, you have much fewer substructure compared to cold dark matter. In the self-interacting dark matter case, it's slightly difficult to see this by eye, but if you stare at the like long enough, you will see the density peak at both the center of the halo and also the peak of subhalos are slightly less peaky compared to a cold dark matter. And that will also influence how a galaxy forms in those substructures. And so we believe by understanding the population of dwarf galaxies in this kind of systems, we will be able to put constraints on these different kind of models. So what is dwarf galaxy we're talking about? Some of these are actually very close to home. And so here's a picture taken from the in Chile near the Blanco telescope. You can see our beautiful Milky Way Galaxy on the sky. And you can also see the large and small Magellanic clouds. And so these are the 2 largest satellite galaxies that are orbiting our own Milky Way. They are living within kind of the Milky Way dark matter halo, which is like much larger than the Milky Way galaxy itself. It's about 10 to 15 times in size larger. And so the smaller galaxy, these 2 galaxies are gravitational bound to the potential of the dark matter halo and are orbiting the Milky Way. And so this is like 2 of those galaxies that we can even see by eye in a very clear sky. And there are many more in the Milky Way, much fainter than these 2. They are orbiting the Milky Way. So here is another picture of the same thing, but I mean in a, I guess, illustrative way. And so you can see LMC, SMC, the large and small Magellanic clouds that I mentioned earlier, and many more satellites that we have discovered today orbiting the Milky Way. On the right-hand side, I'm showing you a picture of a simulation that I ran earlier. This is the Milky Way-sized dark matter halo. And as I mentioned earlier, the Milky Way galaxy itself is much smaller compared to the size of the halo. And so these substructures, which we believe to host like for satellite galaxies like LMC and SNC, are orbiting the Milky Way. And so by comparing what we observe and what we simulate, we are hoping to connect the satellite galaxies that we observe with this substructure and then put a constraint on the dark matter physics. But again, one of the difficulties is to really connect this particular realization of the satellite system with the simulation. How do we know the Milky Way is a representative, I guess, galaxies in this halo mass range? In fact, in this simulation that I ran, we actually ran about 45 simulations. I'm picking just a random 4 to show you. And you can see they actually have all similar halo mass, all these different simulations, but you can see they have a very different halo shape. They actually have very different halo formation history, and hence a different abundance of the substructures. So in order to figure out which one of those are more similar to our own Milky Way, we need that information in order to actually connect the satellites with substructures. And so to that end, I have been co-piloting the Saga Survey. And the Saga Survey is hoping to study satellite systems, like putting Milky Way in a cosmological context. So having more satellite systems to study. And so just to say why this is, I guess, difficult and put Saga Survey in context with different other survey observations. So in the local group, we have the Milky Way, which we live in, and the M31, the Andromeda Galaxy that is our neighbor. They are really close to us, and so we can detect to a much fainter limit. As a result, we can see a lot more satellites in those systems. Like in the Milky Way, I think right now we have about 60 satellites we have discovered in the Milky Way, and about 25 in the M31. Once you move outside of the local group and went into local volume, it becomes a lot more difficult to find the satellite galaxy just because they're much fainter and you need to measure the distance of those satellite galaxies. And so right now, I think there are about 6 to 10. The number is still increasing rapidly of satellite systems that have been surveyed within the local volume. If you go a lot further and go to SDSS, the Sloan Digital Sky Survey, and look at the main galaxy sample, you also find a lot of satellite systems there. But again, these are much further away, and so you can only detect usually the brightest satellite in those systems. And so on average, you can have only 0 to 1 satellites if you use Sloan Digital Sky Survey. And so the Saga Survey is trying to put something in between. And so we are aiming for systems between 25 to 40 megaparsec. And our magnitude limit allows us to probe around 3 to 4 satellites per system. And so we are hoping to obtain 100 systems in the Saga satellite systems of Milky Way-like galaxies from the Saga Survey. So here's just to show you the footprint of the Saga Survey. As I say, we are trying to get about 100 Milky Way-like galaxies. We avoid the galactic plane just because there's high star population contamination for us. Not for others, they are great objects to study as well. And for each systems, then we look into around 0.5 degree in radius. So this roughly corresponding to the viral radius of the corresponding dark matter halo. And basically, we're trying to find satellite galaxy in this field of view. Because the distance is already further than 25 megaparsec, the way that we can measure distance is by using spectroscopic redshift. Tip origin branch or surface brightness fluctuation, they are now applicable at this distance. We can probably use them for since they are within like 5 to 10 megaparsec, but not at 25 megaparsec or further. So in the end, we measure the redshift for each individual galaxy, or almost all individual galaxies within the field of view, to tell if they are satellite galaxy of the host galaxy or not. So this is the Saga Survey in a nutshell, right? So within the field of view, as I showed you earlier, down to our magnitude limit, there's about, I would say, 2,000 to 3,000 galaxies in the photometric color alone. Most of these are just background galaxies. I mean, we know that because the background has much larger volume than since they are in the foreground. And so our job is to find which of those are actually satellite galaxies that are in the foreground, right? They are not background galaxies. Because since in the background are redshift, they have much redder color, you can make a very safe color cut just to remove things that you know absolutely that already redshift outside of the possible color range for galaxies, for dwarf galaxies. And that will give you about still 1,000 per square degree left in the field of view. And so in our first stage Saga survey from 2013 to 2017, we took redshift for each individual object you see at this conservative color cut to obtain a very complete sample for the objects. And so from there, we accumulate a lot of redshift data. And from there, we can actually do a much better training. And also partly thanks to deeper photometric data that later become available, we then can actually improve our photometric cut, both using color and surface brightness, to further reduce the number of object candidates to about 200 per square degree. And so this make our, I guess, observation much more efficient. From here to here, it takes us about like 4 years to get 8 systems to complete. And from here to here, it took us about another 3 years to get, I guess, 25 systems complete. So we are like order of magnitude increasing our observational speed with this improved photometric selection. And in the end, we still obtain redshift for each individual objects for this because they are all possible candidates. So we obtain individual redshift for each of the objects and confirm the satellites. And this is just a set of images to show you why this is really difficult. One of this is a satellite galaxy, a Saga satellite. The other 4 are background galaxies. And you can see just from the photometric image itself, it's really difficult to tell which one is a satellite galaxy and which ones are not. If you are interested, you can guess which one is a satellite galaxy. I can tell you the answer later. So last year, we published our stage 2 result, which we have 36 Milky Way system we fully surveyed. And so you can see here, this again, field of view of the corresponding halo radius, and all the colored circle are satellite galaxy we found. You can see that in some system we have very few or 0 satellite galaxy we found down to our magnitude limit. In some systems, we have like 9 or 10. So this gives us a configuration space, and the color is actually the line of sight velocity. So it gives us some idea of the configuration and the velocity distribution of the satellite in these systems. Here is the image of the individual satellite we have discovered. Each group is one system. So again, you can see systems with 9 or 10 galaxies and systems with 0 galaxies. You can see a wide range of different morphologies of the satellite galaxy. You have things as bright as like the Magellan clouds, or even more structured than the Magellan clouds. And you have this very tiny, irregular dwarf galaxies, like little blob in the systems. You have a wide range of dynamics of these satellite systems. So there is a rich galaxy formation and galaxy evolution science we can actually study of these objects. I will touch this only briefly, but I want to go back to my original talk about how do we use this to study the nature of dark matter. So you can see for each group, we can count the number of satellites. And actually the satellite here is ranked by their luminosity from bright to faint. And so if I take the luminosities and plot the luminosity function, like the number of satellites a function of luminosity, this is what we get. Here, the color is the same set of color that you see earlier that I used to group each objects. So you can see you have system with 9 or 10 satellites to system have 0 satellites. Again, this is observational program, so there's always some incompleteness, for example, the ratio failure. And so all the incompleteness are modeled in our program with this shaded region that you see here. And so from here, you can see the Milky Way luminosity function, which is this line. It's pretty much, I guess, typical compared to the set of Saga luminosity function. There is actually an interesting thing. The fact that you see this like a rainbow color is actually interesting. It actually means the set of luminosity function do not cross each other that often. So the systems that have more satellites also tend to have more bright satellites. And this is actually expected in structure formation if you only think about dark substructures. But the fact that when you see look at the satellite distribution, they also follow. It actually means that the satellite actually follow the ranking of the halos quite closely. Like the stochasticity in galaxy formation function is not enough to totally erase the self-similarity in the subhalo distribution, the subhalo luminosity, the subhalo mass function. So here's another way to see a similar thing. So this spread in the luminosity function, they are correlated with the host galaxy K-band luminosity. So this is the number of satellites as a function of the host galaxy K-band luminosity, which is a tracer for stellar mass. And we also know that it's a correlation with the dark matter halo of the system. And so you can see there is a kind of a correlation there. Kind of we expect since they're brighter, are more massive, and hence they host more satellites. It might be interesting to know that the correlation is actually even stronger if you correlate with the brightest satellite. And this is related to what I say. This is what you actually expect in traditional structural formation of dark matter universe, where the brightest satellite kind of dictate where the normalization of the subhalo mass function is. And so the fact that we also see that in observation is really interesting and confirm our theoretical prediction of that the satellite follow quite closely with the subhalo mass function. So keep moving on to how do we use that whole information to constrain dark matter. So I'm going to take a step back and just demonstrate how do we do this within the Milky Way. And so this is a series of work led by a student who I also co-advised at Stanford, Isa Neller. We use the satellite discovered by Sloan, all the classical satellites discovered by Sloan, Pan-STARRS, and Dark Energy Survey DES, and then jointly model their distribution within the Milky Way. And so we start with the suite of simulation that I ran earlier, and then we apply a satellite model. So the satellite model is a connection of substructure to satellite galaxies, mostly based on subhalo abundance matching. So that is the empirical model connecting dark matter halos and galaxies. But we include a few recipes to take into account, for example, the disruption due to the central galaxy of the satellites. And so it's slightly more sophisticated than planet abundance matching technique. And then from there, we apply then to the Milky Way satellite data and compare between the data and the model prediction. And so we run a Monte Carlo, microstream Monte Carlo in order to get a full prior distribution. And so the documented part hasn't come into here, right? This is just model, kind of constraining the satellite model itself. And then we repeat this analysis with different documented model. And so from there, we are kind of jointly constraining the satellite model parameter and the different documented model. And in the way we marginalize over the satellite model parameters to get a constraint on the documented model. So here is a demonstration of a work that we did with, again, this is with Milky Way satellites, not with the Saga data yet. And so on the left, you can see what the model predict between the stellar mass and the halo mass relation for the Milky Way satellite. So this, to read this plot, is basically saying that we discovered the smallest satellite we discovered in the Milky Way has about like 200 solar mass and stellar mass, and we predict their documented halo mass is probably about like 5 or 6 times 10 to the 7 in halo mass. You can see this is larger than if I naively extrapolate like a fit from the bright large scale structure. And so it kind of reduced our constraining power on documented halo model. And partly it's because you have to marginalize some of the uncertainty in the satellite model. But anyway, we do get some halo mass, right, using this model. And from there, then you can put constraint on documented because for a class of documented model, like one documented in particularly, it basically suppresses the small scale substructure. And so here on the right, I'm showing the transfer function of, for example, one documented model and a few others. And so basically what we're trying to do is to say, for this particular model, if I discover a satellite in this halo mass, can I exclude that model to a certain confidence level, right? And so if I discover something at 10 to the 7, I can probably exclude this particular model. I should also say that this plot is plotting with specific parameters. I'm not saying that I'm excluding all fuzzy documented. This is just for a set of example parameter to demonstrate how this procedure works. So where does the Saga data come in? So some of the uncertainty you see here partly comes from the uncertainty of where the Milky Way is compared to the simulation, right? As I mentioned, the Milky Way has its own unique formation history. The presence of M31 and the Large Magellanic Clouds also put uncertainties on the satellite population. And so part of this comes into the uncertainty in our model. So the Saga survey, what the Saga survey provides is to kind of calibrate where the Milky Way is and understanding how the formation history and, for example, the environment, large satellites contribute to the overall satellite population. So we are trying to do a joint fit with all the Saga data with the satellite model. We haven't done that yet, but here is what will happen if we take the best fit model to the Milky Way and just apply it to the set of simulation that we ran, right? So this has a course of different simulations of different formation histories and different satellite population, and make a prediction of a Saga-like observation. So the stars here is the actual counts of number of satellites, a function of how many systems. So this is, we have 3 systems of 0 satellites, 1 system, 3 systems, 1 satellite, etc. And then we can make the same prediction from the suite of simulation that we ran, applying the satellite model that best fit the Milky Way. And see, right now what we see is that they are roughly consistent with each other. And we are hoping to do a joint fit to get to the bottom of this and put the Milky Way into the context of the Saga observation. You can also see we still have quite big uncertainty due to the limited number of observed systems. In Saga, we have 36. However, we are on track to get more. So I would just say very rapidly that the Saga survey, in addition to documented science, is also very interesting to study galaxy formation evolution. And so here you are looking at the quench fraction, or the number of non-forming star satellites to the total number of satellites as a function of stellar mass. And you can see the Saga point is roughly here, and they are kind of lower than the Milky Way and M31 satellites. And so this has been, we have found this in our first stage result, but now we have a lot more data. We still see the same trend persists. And so this is something that's interesting, and we are eager to investigate what this means to us. And we have been working with people running hydrodynamic simulations to compare our data with prediction from hydrodynamic simulation. This is one example from Atkins from the embodied shock group of the hydro simulation. And as you can see, the Saga data kind of actually lie in between some of their simulated data. So this is one of their simulation, goes from here to here. The other side goes from like here to here. So maybe the different hosts actually produce systems with very, very different quench fraction in their setup population. I'm going to skip this slide. And so I mentioned that we have 36 hosts right now. Actually, as right now, as the time I'm speaking, we have 75 systems that we have completed our survey. And we are expecting to complete the full survey to reach 100 hosts by the end of this year and publish our result, late this year or early next year. And particularly, we will also discover about 50K redshifts that are newly collected by the Saga team. And this redshift will also have a lot of additional science that we can do with that. Currently, we don't plan to expand the Saga survey. So the Saga survey will kind of come to a completion by the end of this year when we reach 100 hosts. But it's good to think about what's go beyond the Saga survey. And in particular, as I mentioned, we have tons of redshift that we collected in Saga survey that serve as practically training data for very low redshift universe, because the Saga survey is focusing on like 0.1 in terms of redshift, right? So this is the redshift distribution, and this is where the Saga satellite lies. So we have actually been quite successful in obtaining like spare fibers in other programs to just do a very low redshift survey. So in particular, we have been working with the Southern Stellar String Spectroscopy Survey, or S5. We just put in spare fibers using the Saga photometric selection and trying to get, in this case, isolated very low redshift and faint dwarf galaxies. And we will be able to compare the self-formation history of those isolated galaxies and satellites. We have also been able to convince DESI to give us some their secondary targets in the program. I think they are actually going to have a survey, like starting one of our program this week. And again, this will survey a large portion of the sky. And we will get a lot of, we are hoping to obtain a lot of very low redshift galaxies. So by very low redshift, I mean redshift less than 0.03. And that map out the local universe down to like stellar mass of 10 to the 7-ish. And in the future, I'm hoping to lead this program using the Vera Rubin Observatory LSST data sets. And in particular, I'm hoping that we can use the data we have collected through Saga and DESI and develop something like a photometric redshift algorithm that actually works well in the very low redshift region. This has been very difficult for regular photometric redshift, not because of the algorithm, but because of the lack of training data. And so the hope is that with all the data we have been getting, we were able to create something like a photometric redshift algorithm for the very low redshift universe. And that will help us to map out the very low dwarf galaxy in the universe and map out the structure at that particular stellar mass range within the local universe. And that will actually help us to understand dark matter. And so this is, as I mentioned, as Sherry mentioned, I'm leading the dark matter working group in the dark energy sense collaboration, right? And the reason I want to map out local universe in this Rubin LST data set is because they will help us to measure the minimum halo mass in the local universe. And also we can use those very low redshift dwarf galaxy as lens and measure the weak lensing structure of these dwarf galaxies. And that will actually allow us to measure the halo profile and shape that particularly sensitive to the self-inherent dark matter models in these dwarf galaxies. So with that, I'll just put up my summary and take any questions that you might have. Thank you.
I'm just going to clap for everybody. Sorry about that Zoom version of clapping. Thank you so much for giving us such an amazing talk. We're gonna open up the floor if we like for questions. I know people can get very excited. Amio, you have a raised hand. You want to go ahead?
Sure, yes, I do. Yeah, thank you. That was really fascinating, and this survey is really interesting. I have two questions. One is beyond just distinguishing between warm dark matter and cold dark matter, can you use this survey to distinguish between cold dark matter particles? That's my first question. And my second question is, can you use the survey to estimate the total virial masses of the parent galaxies around which you see the dwarfs?
Yeah, thank you. So the first question, between different cold dark matter scenario, it's difficult to use galaxies to distinguish them. Like if they don't actually have imprint on the underlying structure of dark matter, then it would be difficult. So for example, if we are talking about WIMPs of different different masses, that would be difficult to tell from a galaxy alone. However, I also think that understanding the galaxial connection better will help us in other experiments. For example, if direct detection is going to measure different cold dark matter particles, right? And that also requires a better understanding of, say, the dark matter halo of the Milky Way itself. And that is where this kind of starting galaxial connection can help. And the second question, yes, certainly the satellite can tell us a little bit about also the galaxial connection of the host halo. So this plot I'm showing here, for example, this is all the velocity colored by the velocity of the satellite. So that will give us some dynamical mass of the host galaxy, so host dark matter halo also. Now this is only line of sight velocity. We don't have the transverse velocity. We are also hoping to obtain dynamical mass from gas of all these individual systems. We will want to do a follow-up program of this. And then actually we can then compare like the dynamic mass from gas and dynamic mass from satellites. And that will also help us to learn a little bit more about the dark matter system of the entire system.
Thank you so much. And I just wrote down the sequence because there's so many questions, there's so many raised hands. So I just wrote them by according to like the time they pop up, at least on my screen. So Rachel, please.
Thank you. Thanks, Yao. Great talk. Great stuff. So I'm really intrigued by the fraction of quenched satellites. That's always been one of the most interesting results to come out of Saga. And so it's interesting to see that persisting. So what I'm wondering is, now that you have this beautiful suite of simulations where some simulations are showing a high quenched fraction and some are showing a low quenched fraction, can you go in and tell us why you're getting those results? Does it have to do with the orbits of the satellites? Does it have to do with, you know, something to do with the cosmic web or the orientation of filaments? What is the physical cause of this result in the simulations?
Yeah, certainly. Thank you, Rachel. And this is also one of our most, I guess, interested questions come out of Saga Survey. So as you can see my note here, I would say my first guess are either the environment and or the burstiness in star formation history. And the reason is that, well, so first of all, we definitely want to do this, but it's still a little bit difficult at this current stage, just because actually the simulation, we don't have a large number of populations. So you can see there are 4 here. We are actually also excited about the TNG50, which is coming out just recently, and want to do a comparison there as well. And but I think by the end of we have the 100 system, we will also have a lot more simulation that we can compare with. Among the objects that we have compared, so I'm working with Alison also about this. Environment definitely seems to have some impact. So for example, if we see you have a companion, M31 like companion, or the host itself is older, like formed earlier, it does seem the satellite are more quenched. But this is not yet statistically significant, just because the number of systems. We also found the burstiness quite interesting, because in some cases, we just don't see any correlation between the systems that are more quenched and less quenched. And we were just wondering if that could be just due to the burstiness, like we happen to see a snapshot of things that they are quenched. And so for that, we can also actually just estimate a fraction of, more quenched systems and compare with, quench time scale and see if burstiness can be explaining those things. So this is one of our top priorities in the upcoming study.
Great, thanks, Yao, that's fascinating.
Thank you. I think next up is Alberto.
Hey, thank you, Yao, for for the talk. So just a very basic question. Do you see, have you analyzed the data for the presence of favored planes and given that you have the kinematics and the distribution of the satellites, and do you see a relation between that and the spin of the central object, etc.?
Great question. We don't quite, yeah. So, okay, so just let me recap for people may not, if you're not familiar with, there has been this very, I guess, heated discussion about whether there's a planetary structure, like in the Milky Way M31 and many other satellite systems. So in the Saga survey, we did like another study, which we look at the satellite pairs, and then we plot whether they are moving in the same direction or the opposite directions as a function of their opening angle. So this means the two satellites are on the opposite side of the host, and they are moving in the opposite direction. So they are co-rotating and the other way. So this means the two satellites are on the same side, and they are moving to the same direction. And so you can see the Saga points in green and blue bands. They are just satellites. They are in the inner region or the outer region. We don't really quite see a very strong signal, as you can see. There seem to be some, I don't know, actually, this is a plan of satellite or more like co-rotating pairs. We see a few satellites that are really close by, and they are moving to the same direction. So I can, actually, let me just jump back to this. Like you can even see some of this here, right? So like you can see like this pair, they have a similar velocity and also very close to each other. You see some of the pairs here, they are very close to each other and have very similar velocity. And just you can draw by eye like a few like this kind of pair. And that is what like drive the bump that you see earlier. But otherwise, we don't see a statistical significance of a plane of satellite for now.
If you run the same test on the simulation, so you get anything different? Or?
So that is a heated debate, I guess. So my own study of simulation that I ran, we don't see a signal of plane of satellite. But there has been debates about like whether how you do statistics and whether like if you plot the statistics in a certain way, you will see a signal or not see a signal. But so far, I haven't been able to find a strong signal in simulation that I have ran.
Okay, thank you.
Thank you so much. So who's up next? Layman.
Hi, thanks for the talk. You mentioned the DESI secondary target program, which seems great for this application, and I was also wondering within DESI if the Bright Galaxy survey would let you do some of this as well, maybe extend it to a little bit higher redshift.
Yeah, certainly. So we are obviously working closely also with other people in the Bright Galaxy survey. And so just for context for other people, if you're not familiar, the Bright Galaxy survey roughly go down to orbital magnitude of 19 to 19.5. And the secondary target we put in roughly cover from the range of 19 to 21st. And so the fact that there's a small overlap is indeed to just compare notes between the Bright Galaxy survey and our survey. The Bright Galaxy survey is trying to be more complete in terms of everything to the magnitude, and the particular lowly survey we are doing is only going to survey the low redshift universe. So we are not doing high redshift stuff. The other thing to know is that Bright Galaxy survey is done in bright time, and so the secondary survey we are doing is at dark time, so that because it's phantom. But definitely the hope is to join all the information we have available. Including the Bright Galaxy survey and the lowly secondary target program to understanding the evolution of galaxy.
Great, thank you.
Thank you. I feel like I want to jump in with a quick question, but Josh, you can go first if you like. So I'm the host, I can go last.
Sure, thanks, Shirley. Yeah, thanks, Yao, for a great talk. So I just have a quick question about like these. So have you ever considered looking at the halos that are lower than like 10 to the 6 solar mass? Because I think co-dark matter scenario, there's going to be lots of these small lumps. And would it be interesting to also worth studying in this survey?
Yeah, so I mean, obviously in the Milky Way, we will extend this with, for example, LST data. We'll definitely extend this within the Milky Way. outside of Milky Way, it's going to be really difficult, right? So the program right now, we are trying to calibrate the Milky Way using the bright end, just because the satellite function is a very nice, self-similar function. So you can calibrate the amplitude using the bright end. But if we want to go to below 10 to the 7 in stellar mass, in halo mass, that means you are talking about 10 to 100 solar mass in stellar mass. That is still prohibitive right now for things outside of the local group. But yeah, we are thinking of this. We have been talking with people on doing follow-up observation using HST in specific Saga field. We are talking about using PFS on doing, again, a target observation for one specific field, but it's difficult to do for more survey for more system at that magnitude limit.
Thank you.
Anyone else want to ask a quick question, or I can start with my first? All right, yeah, you simulated like 45 galaxies to compare to our Milky Way at the beginning. And then, the question I had in mind immediately was, how do we know for sure we've simulated enough sort of diversity of galaxies compared to our Milky Way? And what would be your dream number of galaxies you feel like you need to generate? And that relates to another question, which is for this program to work to understand the properties of dark matter, we kind of need to understand the degeneracy possibly between the galaxy formation history and environment with the properties of dark matter, and what your plans on that direction.
Yeah, great, thank you. So the first question is on the number. 45 is not too bad. I can say we started to want to do 100, but in the end, we found that actually what is more important is to characterize how the amplitude correlate with a specific property of dark matter halos. For example, how the satellite amplitude correlated with formation time, correlated with the shape or the density of the dark matter halos. Once you characterize this, because in cold dark matter case, they are really self-similar. They don't actually, adding more system doesn't really add a lot more, information on that particular part. However, that said, we are running a suite of simulation that are more specific to Milky Way. Like we want to understand a few other things that Milky Way might be different. For example, the existence of LMC. We have found that the existence of LMC seems to be playing an important role in terms of the total satellite population. We also see that in the Saga data set as well. And so we are running a set of simulation which have like a recent accreted bright satellite. And hopefully that will also add to this suite and span a wider range of Milky Way-ish galaxies and halos. The second question is, how do we break the degeneracy between, galaxy formation and dark matter models? This is one of the biggest challenges in this program. And so our hope is that this kind of satellite model that I talk about, they act as like a layer that you can marginalize over, and their prior can come from independent observation and or hydrodynamic simulations. So you can think of hydrodynamic simulation being realizations of specific physical models. And you can, depending on your belief, right? Say if you trust certain hydro simulation, those then give you very strong priors on this satellite model in your program. And then so you got much better limit in your dark matter in your dark matter constraint. Or you can say, well, I don't fully trust the hydrodynamic simulation, but I got, 5 different hydrodynamic simulation with slightly different star formation prescription. And I will take all of this as a prior. That will obviously weaken the dark matter constraint, but you have a higher confidence of like you marginalize over a broader range of galaxy formation physics. So this is the program I'm having in mind. And so we are hoping to both using like independent observation on galaxy formation itself, both from the Milky Way, outside of Milky Way, and also from hydrodynamic simulation to construct the priors for these empirical models, and then marginalize it to get constraints like this.